very much for the introduction. And thanks everybody for coming so early after a happy dinner yesterday evening. And so I will just start by repeating the. So today I will focus on the case where the group mostly is the unitary group. Just to afterwards say a few words to the case where this is this here, UN tensor I between 1 and so in this case I wrote the Weingarten formula, which was as follows. Concrete one was that if I want to integrate over UN ui1j1 uik jk u conjugate I prime 1 j prime 1 u conjugate I prime k j prime k. So we made the case that in principle we would be interested in knowing the integral for an arbitrary number of u and an arbitrary number of u conjugate, but actually as soon as these numbers are going to be different, the integral is going to be 0. So the only case of interest to consider without arbitrarity is that one here. And that one is actually a sum, as I wrote, over all. What we have is we have to look at the pairings between row indices of u and of u bars, which I call sigma, and pairings of column indices of u and u bar, which I call tau. So u sigma tau, which so pairings here, since it's between some u and u bar, can be labeled by a permutation. The permutation on SK of delta I prime sigma delta j prime tau times this Weingarten function of sigma tau and n. So again, here the definition was that this is the product for, let's say, L between 1 and k of Dirac IL I prime sigma L. So I'm checking if I1 equals I prime sigma 1 and so on and so forth. So I'm doing it k times, same definition here. And that one here, I also mentioned it briefly, but I would like to get back to it because the next step will be to somehow here I have a permutation, so I have a group structure, and I would like to use this to make some calculations. So this function here, just reading somehow and just applying the formula which I described the other day concretely was so WG of sigma tau n. If I write it as a matrix, it's like a k factorial by k factorial matrix in principle. That's the inverse of the matrix where have scalar product of sigma and tau. Inverse. This was the gram matrix where I think of this here as elements of Cn tens k plus k. And what could be, so remember this was something like this, like, let's say here k equals 3. If k equals 3, like maybe the identity would be the one which links ones to this one. It would be like sigma equals to identity. And maybe and now if I take tau is maybe the region which swaps 1 and 2. This would be maybe this guy here. So 1, the first one, I'm checking if it's matched with the second one with the first one, and third one is, is unchanged. So now if I want to know, remember again that here, this means something like this. This means like, this is sum of over, let's say, L between 1 and 3 of, sorry, maybe I would say like L1, L2, L3 between 1 and n. It will be EL1, times EL2, times EL3, times EL1, times EL2, times EL3, where this is the canonical basis of the of Cn. So this is, that notation is probably lighter than this one. And in view of this, you see that since this is an orthogonal basis, canonical orthonormal basis each time, you see it's the scalar product here in this notation, sigma. Oh, it's a direct computation from here that this is n to the number of loops of sigma tau inverse. Okay. So you just have to, like, one loop of sigma tau inverse will give you n possibilities of indices, and this basically describes the degrees of freedom left in this sum. So maybe one observation here is that actually the Weingarten function of sigma tau n actually only depends on the conjugacy class of sigma tau inverse. The conjugacy class in the permutation group, and this is why it's because the product is commutative. I have a commutative product. I want to evaluate U11, U22, blah blah. It's like evaluating U22, U11, blah blah. And then what happened is that I actually conjugated this by the reordering of my function. So and out of this actually we have a nice group theoretic interpretation. So group. So somehow the next step is to try to understand this Weingarten function. If we want to do some asymptotics, I have some Dirac things here, so I have to maybe to count some objects. But then I have a weight, and I want to understand how the weight behaves as n goes to infinity. For this, I should try to understand this function. There is a little bit of work to be done here, and if I write it in a group, a theoretical setup, so probably it would be nice to use the notion of convolution over a group. I am more used to using the group algebra notation, so this is what I'm going to do. So see, I'm taking that, I would say that C of Sk. So here you put any finite group would be okay, and the algebra is just the span of so this is the span of lambda sigma for sigma in the permutation group, and the multiplication is lambda sigma lambda tau is lambda sigma tau. Again, that's the convolution on the function algebra if you prefer. And what we have there is if we introduce this function, let's see. Okay, so I will call it G. That's so G is an element of the group algebra of the symmetry group, which is sum over all permutations of lambda sigma times n to the number of loops of sigma. And what I have is that, so this is just really, if you think about that point and the meaning of the inverse, what you can observe right away is that the inverse of G, which obviously I'm going to define as W, this is actually, I can write it as sum for lambda in the symmetric group again of the Weingarten of conjugacy class of lambda and delta lambda. So I make the inverse in the group algebra. Then the coefficients which show up if I decompose in the canonical basis is this one. So at the end of the day, I managed to compute this with some group theoretic formula. So if you want to compute explicitly W, this gives you a formula. I'm not going to write it down, but I think there are many people here who are experts in representation theory of the symmetric group. And an observation here, which basically flows from here, is that observation. We have that G belongs to the center, actually, of the algebra. So it's a central function. Just by some character analysis, you can compute what is G, and then its inverse is very easy to compute. This gives a formula. This gives a formula for the Weingarten function. But this formula is actually not very useful. I mean, it's not very easy to deduce, let's say, asymptotics. Yeah, so actually the formula is, try to see if I remember it. The formula is the sum over all irreducible representation of the symmetric group of the character of sigma times the dimension. There is a dimension factor, and so there is a yes, dimension of and then you have maybe there is a square here, and there is a 1 over k factor, something like this. But anyway, so you have a formula like this, which you can get by the non-commutative Fourier transform. So I think it's correct, but double check on actually. So I wrote it in one of my earlier paper, but it happens it had been written also by a paper of Zuber in around 1980 as well, following up on Weingarten. Again, like one of these instances of people from two worlds ignoring each other for way too long. And all right, but if you have this is not so convenient again to understand what happens as n goes to infinity. And so here are some strategies actually to understand the large n behavior. The first, the naive strategy is to say that if I look at, if I write n to the minus k g, the number of loops. I mean, I said something like this yesterday, but I'm just rephrasing it somehow. The number of loops is a number between 1 and k. So, and it will be maximized if sigma is the identity. So just rephrasing it here, I have the identity element plus n inverse times sum for sigma, not the identity, of lambda sigma times n to the 1 minus k plus the number of of loops of sigma if I didn't mess it up, and that should be a positive number here. So what we are doing basically is, I just call it x, and now what I will have is that I will have that n power k times the Weingarten function. This is going to be lambda e minus n inverse x plus n minus 2 x squared minus n minus, and so on and so forth. That gives me a formula for the Weingarten function. And actually, this one is already reasonably efficient in the sense that this gives the right, the right asymptotic order. So it's naive, but well, it's naive, but it gave me a job first, so I'm happy that about that. And also it already unveiled some important phenomena, like the fact that this Weingarten function of sigma and n behave actually. So the leading order is this Mobius function of sigma times n the minus 2k plus number of loops of sigma times 1 plus O of n. So these kind of things were known, where this is here Speicher's Mobius function, non-crossing Mobius function. So probably some people will speak about, if I understand correctly, we'll speak about more about free probability tomorrow. Yeah, I'm not going to define, but this is it's up to some sign. It's a product of Catalan numbers. Maybe I can just write it like so. This is plus or minus a product of Catalan numbers. So already out of this, you can deduce this information, this interesting information, including the leading order here. One problem. Why do I say this is naive? It's because we don't get the right radius of convergence. So, I mean, with the right estimate. Actually, this is a correct formula. So the radius of convergence should be correct, but you see, when you try to understand, this is you could think of this, if you want, you could think of this as a formal power series, right? You could think of this as all this as being elements actually of the group algebra. It's not over the complex field, but rather over the power series in n inverse. And you are taking inverses in this over this ring. And when you write it like this, this is that's actually a rigorous statement. But then when I want to understand, let's say for a given sigma, what is the, what is the 1000th coefficient which arises here or so, there is a formula, but the fact that this is a signed formula implies that the naive estimate on the size of this coefficient is not the right one, actually. And the way to fix this problem is actually to break the symmetry, so to take an order, as Jamie was suggesting yesterday. So here, everything is happening. You see, this is a central function. So here, everything is happening in the center, but the center estimates again are not so good from the point of view of analysis. So the solution actually is so the strategy number 2 actually is to do the following. So is to observe that G is actually equal to n times lambda e times n times lambda e plus lambda 1, 2 times n lambda e plus lambda 1, 3 plus lambda 2, 3, and I will write one more. And no, what is 2? Lambda e. Lambda e plus lambda 1, 4 plus lambda 2, 4 plus lambda 3, 4, and so on and so forth. So this is actually what are called the, I'm not sure what is the good notation, but this is here, these are the so-called Uchis-Murphy elements. So this is, maybe this is Uchis-Murphy elements, maybe 2 in K, and then this is Uchis-Murphy element 3 in K, and so on and so forth. So and if you just calculate, you see that this is a correct formula. I think that this thing was first observed by Jonathan Novak in that way, a kind of breaking symmetry, but of course, if one looks at the representation theory of the symmetry group from the Vershikov-Kunkov point of view, that's actually a very natural way to do. You're just approaching it by some kind of maximal abelian subalgebra paradigm, and that's actually what ought to be done. You introduce this order between 1 and n, and you make the decomposition that way, and then, of course, what you have to do is, well, then you're just going to write that G inverse is the product of inverses. Maybe you have to revert the order, but anyway, this gives you a formula for Weingarten, and in particular, out of this, so if we read, so reading from this formula, what we get is that Weingarten of sigma n, this is actually the sum over all ways I can write sigma as I1, J1, IK, JK, where so these are transpositions. So all these are transpositions. in the symmetric group on k elements with the property that, well, so I'm always asking that, J1 is bigger than I1. So IL less than JL, and JL is weakly increasing, so JL less than JL plus 1. So if you just apply this strategy here, pointwise to each of these people, and then you see what this multiplication means. This is what you should have here with a minus n. Okay, that's also it's a very clean formula, and something else actually, right? So something else is that this minus sign here is actually an overall sign, because of some signature consideration, and the number of solutions which you will have here always have the same parity. And out of this, you can actually recover also rather smoothly this formula which was here. So okay, so maybe so maybe just to recap what was here. So the con of this, the demerit, as one says in Japanese, of this formula is that so you leave the center. You have to go outside of the center, and the merit, the pro, is that well, we get an overall non-sign sum. It's signed, but the sign is overall the same. So which means that we get the right we get the right radius, the correct.
Overall, you mean you could
yes. Yes. Yeah. Yeah. So let me try to make the statement rigorous. Rigorous. That's correct. But if I wanted to rewrite it, what I could do is I could erase this and have outside -1. -1 to yeah, so I would have like the signature of sigma. Yeah, that's it. That would be it. Yeah. All right, and what I am going to do actually now is look again at this formula from now what we have is we have to this is what I like to actually, yeah, this is what actually Matsumoto and I like to call a path between sigma and E. So I think that really this formula was probably we should give credit to Novak for this formula, but working on from a different point of view with Matsumoto, we rediscovered this formula actually just by using the orthogonal relations of the unitary group and applying them to the Weingarten function. We rediscovered a similar formula, And we actually discovered that somehow Weingarten already knew this formula, even though it was written in such a way that it's only after having rediscovered it twice that actually this is that there was some kind of past interpretation. So anyway, some people before had something similar, and some people after had something similar as well. And now what I would like to do is start to speak a little bit about fluctuations. And for this, I will just do some mind experiment for now, which is to look at a similar formula, but I'm going to add. Now I'm going to add in the game. I'm going to consider a partition pi of the set of pk. This is a partition of k elements. This is some blocks which are going to think of an equivalence relation on k elements. And now I'm going to consider sigma and tau, two permutations of sk, which have the property that they leave pi invariant. So sigma applies acts also on the partition, and it doesn't move the block. So like the cycles of sigma are inside each block of pi. And now what I would like to do is, so I'm just going to remove the conjugacy class to get back to my original problem of matrices. I'm going to introduce this function here, wg, which is going to depend also on pi, and this sigma, tau, and n, and that's going to be the same. The sum is going to be the sum of pass from sigma to tau, which means here that I would like to have something like a sigma. It could be the other way around, that doesn't matter for me. So I'm not going to bother about I1, J1, IK, JK, tau, with the same properties here. IL less than JL, and JL less than or equal than JL plus 1 of minus n to the k. But in addition, I'm going to assume that IL JL also leaves pi stable. So it doesn't travel from one block to the other. And in this case, okay. First of all, if I didn't have this, what I would have here in terms of integrals, it would be something like this. It would be something like u I sigma 1 I tau 1 u I sigma k I tau k. This would be the integral of this function, and that I would be considering if I didn't have this. Because the only pairing that works for this one is this. I mean, this was constructed by definition, basically. And now, if I add this in addition, what I have is, or maybe I will just give an example where pi has two blocks like this. It doesn't have to be like this, but just to explain what's going on. And what we have actually in this case is that this becomes a product of two expectations where people are independent on each block. So this becomes two independent copies. So independence copies of uij per block. And the reason is because when I leave each block stable, I have a product structure which appears basically, and that's going to be very important for us in the future. The fact that we have this product structure. So let me explain what we can do with it now. Time for the erasing break. I know I should have one in each hand. That's how it should work. Okay, and that's going to be useful when I will want to take cumulants of Weingarten functions, which is what I want to speak about right now. So I'm not sure that the definition of cumulants was introduced, so I will introduce it briefly. So classical cumulants. Of Weingarten function. So here what we do is we take x1, xk, some random variables, bounded, let's say. And we use this notation that e pi of x1, so, and pi is a partition. Pi is a partition on k elements, and e pi of x1, xk, that's the product over all the blocks of pi. Maybe we'll call capital B a block of pi, and then that's the product of elements inside the block of the expectation. So maybe just to give an example, if a block is like this, then e pi of x1 down to x5, the expectation of x1, x2, x3 times the expectation of x4, x5, something like this. And so we have this notion of being more refined. So pi prime is less than pi, is more refined than pi if and only if any block of pi prime is contained in a block of pi. And now we just define inductively k pi of x1 xk is defined inductively by e pi of x1 xk is the sum over all blocks wider than pi of k pi x1 xk. That's a triangular system, so you can define it uniquely. And the key feature of this is that mixed moments, mixed cumulants vanish, which means that if, let's say, xi are independent, and that actually starts to relate with what I was mentioning earlier, because whenever I wanted to do some bootstrapping, I had some assumption of both invariance and independence. What we have is that k pi of x1 xk is 0 as soon as two different of x as xi's of two different indices are in one same block. I'm not going to go through all the theory, but that's going to be enough to know that. But this can be computed. There is a very nice Möbius formula to compute this. Won't have time to send things to infinity, but when things tend to infinity, sometimes we have some non-crossing partitions which appear, and then there is a theory of non-crossing cumulants which was developed by Speicher, and which also appears in some of the cases that Luca, Razvan, and I have been considering. But so for now, this is really I think this is the Russian probability school of the 50s or so who developed this, and we're just thinking that you can also view this as derivatives of the log of the Fourier transform of a linear combination of the xi's at 0. But anyway, I'm just sticking to that. And what I want, so what's the relation between this and that? Now I'm doing just repeating the same thing now. Okay, this notation is for cumulant. Actually, it could be a C, sometimes called so K. Yeah. Just a notation. K is a K-linear function in K random variables. Oh, yes. Thank you. Yes. Thank you. And so maybe here, okay. What we would like to compute is again, I have, as before, I have pi a partition of k elements. Did I write it like this? Yeah. And we would like to, we have sigma and tau. which are two permutations which leave invariance phi, and we would like to compute the cumulants of this k pi of there is a small problem in my notation which I just right now, but am I going to fix it or not? No, the fact that maybe I should have a pi prime comma pi here in this definition, but anyway. Yeah. Oh, this is a small k and the yeah, I'll okay. Maybe I will. Maybe I will continue that way, even though there is a slight flow. So the kind of thing which I would like to understand anyway is something like this. So this is k pi of u I sigma 1 I j tau 1 u I sigma k j tau k. I would like to understand the cumulant like that. And what happens is that there would be a formula. Maybe I should fix. Maybe I should fix my definition. Oh, yeah, maybe I should fix my definition. Maybe I will say that this is. So this is what I would like to understand. One n here is the full partition, and what I'm skipping is that actually there is some multiplicativity here. So actually, understanding that is going to be enough to understand all that. At least now it's fixed. And the thing is that this is going to be exactly the same as this here. So there was an n here which was missing, and here as well there was an n inverse. Sorry. Oh yeah. No, yeah. Okay. Sorry. Yeah. Let me fix it. Yeah. Okay. So but yeah. Okay. So there is a. How about that? That looks. I think it looks better now. Thank you. Yeah. So that's going to be the sum over path. Again, path between sigma and tau, as before, and ends so n inverse minus n inverse to the power. So here I will call the length of the path. Okay. And now the new thing which happens if you read off from here is this this is path, which I will write this, that connexify. Instead of writing a complete statement, that connexify. Connexify. By connexify, what do I mean? Here I was requiring that each sigma and tau they don't. If I look at the action of the group generated by sigma and tau, the orbits will be inside. There will be a subpartition of pi. And what I want is that the partition generated by pi and all the elements sigma and tau here generates becomes transitive over the over 1K. So the group, maybe I should write it, group generated by sigma tau and IL JL acts transitively on the set 1K. And what you can rather easily see is that the decay, so we had a decay here. So the leading order, so it was n to the minus 2k plus number of loops of sigma tau inverse. That's what we had from here. And now it's the leading order becomes less. And then this is plus 2 minus 2 times the number of blocks of pi. Because I want to go, so probably like people who are experts in maps, this is quite simple somehow, but I want to go from sigma to tau, which are inside the block, but I want to connect with it, have to travel out and then come back somehow and do it as many times. So this double operation, I have to do it as many times as I have blocks minus 1. So together with Razvan and Luca, we have a formula for the higher order, the leading. We have more actually, but in particular we have formula for the leading order. So I have to say that with this naive formula, I also obtained a formula for the leading order with by using some results of counting maps which had been developed by Bousquet-Bellou and Schaeffer. But actually, well, here we do it directly with this, like, you know, without having a signed sum, which is much nicer in my opinion. And in the 5 minutes left, I will explain a little bit. So, but that's actually already, in my opinion, an important part of our first paper, because all these formulas, the way they were written 15 or 20 years ago, did not involve this this Hurwitz number, this product of transpositions. I think this is much much cleaner that way. I get back to this idea of invariance, which I discussed last time. Actually, what we have is that in the SUN case, so in the UN case, the invariance can be written as something like this, as what I would call trace sigma A. So here, sorry, maybe I will say xi, okay, xin. So trace sigma, I will just define it on an example. So if so, and this will be clearer than what is meant. If sigma is, let's say, 1, 2, 3, 4, 5, this product of two cycles, then trace sigma of xi, and this is well, so this is trace of xi times trace of xi. So I take 5 copies, and I circle around, take the trace, circle around, and take the trace. So in this case, of course, doing this is overkill. So of course, taking the conjugacy class would be enough. And actually, if I take the conjugacy class, that's a complete invariant. But since we are going to actually be interested in the vanishing thing, we want to develop multilinear functions, and for that purpose, it's actually better to work on that. And if you combine the use of this and this and this, you can actually reprove directly. So remember, before I had this, this growth like n to the alpha something. So here, if you rephrase this, what we get is something like trace if I want to do some bootstrapping, and I have 2 or 3 minutes here. So the bootstrapping would be something like trace sigma xi. It behaves like n to alpha times a number of loops of sigma I. So now, what happens? So end of third hour, and now we start speaking about tensors. What happens for UI tens D, which is a subgroup? So this is a subgroup of this big tensor. The invariants, they become something like this. It becomes something like trace sub sigma, again, where sigma now is going to be a d-tuple, the d-tuple of permutations in D. And here I think that's a good way of representing this is, so actually I should take something like k copies of A here, where A, they are all default tensor products. And it's good to represent A with like D legs for input, D legs for output. And what you do is, the sigma 1 tells you how I am going to connect the first leg. Sigma 2 tells you how I connect the second leg, and so on and so forth. So like I would have a sigma 1 here, sigma 2 here, whatever, sigma D here. And let me not go beyond this blackboard. That would want to like the coffee break is more important than what I. Anyway, the thing is, these are interesting scalings for d equals 1. Now the question is, what are the interesting scalings for they are interesting in the sense that we get some bootstrapping. And what are the interesting scalings for bigger d? So I would say we don't have a complete classification, but we have a complete classification if we make some assumption. So one natural assumption that we look at is something like this. This is, we look at trace sigma A behaves like so first some n alpha times k, which is the size of the permutation here, plus some over I of beta times the number of loops of sigma I, and plus some, I think we call it epsilon, some I not equal j of the number of loops of sigma I, sigma j inverse. And we have quite, under this assumption, we have quite a clean classification of what bootstraps, and I will just finish. So of course you could have, there are many more points, but I think this one is quite natural, and a quick mention of why this is natural. So first of all, if I just keep this, it's like forgetting that, it's like neglecting the difference between the big unitary group and the small unitary group, because then they all have the same behavior. However, if I start looking at this, then we start looking at something which we could see as entanglement properties somehow. So in quantum information theory, if you look at Bell states, for example, depending on, the value here will depend depending on whether we have entangled states or separable states. So at least in the case of small rank, this introduces a whole new family of possible behaviors, with each time like interesting leading orders and all that. And if you are interested, please take a look at our 2 first papers. So thanks for your attention. Sorry for being late.